So I want to re-emphasize what we were talking about for these reactions. Again, I kept saying that the coefficients, there's the numbers that are in front. Remember, there's an assumed 1 in front of the oxygen. Those are how we get between atoms. But also emphasize that what we're doing isn't new. We're just kind of building on one idea. So if you'll look at this equation, given 3 grams of hydrogen gas, find molecules of hydrogen gas. Note that it's all hydrogen. This is what we did in chapter 2. So you take your grams of hydrogen, you use the molar mass to convert it into something else, and you see how the units cancel, and we use Avogadro's number to get to the molecules of H2. So this is great. This all works perfectly. It makes a lot of sense. You've done it before. The difference is that now we have an amount of H2 and we're going to O2. So we have an extra piece to the equation. Grams of H2, moles of H2, and then now here's our key point. Moles of O2 right here, and I'm going to circle it. This is what's different. And those numbers are from the coefficients. Notice that number is because of the O2 number. This is because of the H2 number. That's the only thing that's different. You already know how to balance and you all know how to do things. So now what we're saying is, hey, you can move between different parts of an equation, which is kind of the point, because when you do a reaction, you want to get to the end. You want to know how much you need of each part, and then you need to get to the end. And this is supposed to say H2O. So right here, we figured out how much oxygen we needed, and now we're going to figure out how much water we made. We start with our grams, that's the only number we have, and we go from grams to moles. We go from moles of hydrogen, and now we're going to moles of water. See, here's our 2. That's why there's a 2 there. This is why there's a 2 here. And then that's moles of water, so we're canceling those 2 out. I'm going to circle this. Again, this is the new part. And it would have been totally fine to replace this with a 1 and a 1. We use a word when we're talking about product amounts, and it's theoretical yield. So yield, that's just making something, and theoretical means that we've done a calculation here to make this happen. In the lab, we don't just base it on the calculation, we actually go ahead and weigh it out, and we report how much we've really made. Because the theoretical yield is the everything is perfect in the world, the glassware is clean, the compounds are pure, you have perfect technique. The reaction actually wants to happen, and it wants to happen really well without anything interfering. The room isn't humid, you have the perfect atmospheric pressure, everything is perfect. So it's a theory thing. It's not possible. What I can say is that if you were to write a scientific paper and you were to actually report something that was the same as a theoretical yield, everyone would be like, what? Because no one really expects you to get the theoretical yield. You want it to be in like the 90s, but no one expects you to get the theoretical yield. How many moles of water if you have 3.5 moles of gas? So before, up in these examples, it was grams. So this is really easy right here. So we're moving from the H2 to the water. So this is what we're doing. We're moving from him to him. So this is the only number we have. See, we've got moles to moles, and it's wanting to know about water. And if you'd like to remind yourself, this is a place where it's very helpful to write this at the front. And write what you want it to be. And then that gives you basically the same number, right? Because these two cancel. But you could have put them both in your calculator if you wanted to. Now I'm going to pause for a minute and you work this next problem. So I'm going to say how many grams of water. This is the only number I have that's not paired with something else. So like grams and moles are paired together, grams and moles are paired together. That's the only number I have not paired with someone else. So 3.50 moles of hydrogen gas. So there's my moles of hydrogen gas. And this is the point. You can only change to something else on the mole scale. You can't jump to grams. I can't suddenly jump to grams of water. That won't work. You can only do it at the mole level. So moles of water but it's asking for grams, right? Grams. So now I'm going from moles of water to grams of water. Now I look up the equation and make sure I got my numbers right. There's a 2 in front of the H2, and then there's a 2 in front of the H2O. Again, those would cancel. In my 1 mole, I've got 18.02. Notice I didn't need my oxygen in this problem, so sometimes you'll have a little extra information you don't need. That's not uncommon, so don't let it throw you. When you do this math, you're going to get 56.0 grams. It's 1, 2, 3 sig figs because this was 1, 2, 3 sig figs. These numbers right here, that mole ratio, they're considered to be exact. You can't have a half of an atom. You have to have a whole atom or no atom at all. So that ratio is an exact ratio of atoms, so it doesn't matter. And these are so far out, you know, it's to 2 decimals. They usually also don't matter because you're using a big enough periodic chart. You're going far enough that they aren't going to affect the significance. But always do a quick scroll through and just make sure. But most of the time, the numbers of sig figs are going to be coming from this one. All right, next problem. So now this one is asking for grams of water, and this is very typical for what you're going to need to be able to do in the problems and in the lab. How many grams of water will produce from the complete reaction of these grams of hydrogen gas? We still need that reaction up there. So this is the only number that has a unit that's not paired with something else. These units are paired together, so you don't want to start with something that has a paired together unit. Grams of hydrogen into grams of hydrogen. It's funny, there was a typo there. And then we're going to go moles of hydrogen to moles of hydrogen. And then here's our point at which we can change to someone else. You could like go off and take it to use Avogadro's number and go somewhere with it, but they're not asking about the hydrogen. They're asking about the water. You go from water to moles of water to grams of water. All right, so then last problem, I'm going to pause and you work the last one. So you should have started with, again, the only number that's not paired, with a unit that's not paired to something else. Make sure you're labeling all of these things as oxygen or hydrogen so you can keep up with it properly. So grams of oxygen into moles of oxygen, and then moles of oxygen. Again, you could go other places from here. You could go back to grams, but that's not what they're asking. They're asking you to go to another part of the equation. So again, it asks for the grams of water, and this might have been helpful if off to the side you'd written grams of water. So you know that's where you're headed. Then you're going to go from moles of H2O to grams of H2O. This number should be 32 grams per mole. So in 32 grams in 1 mole of O2, there are 1 to 2. Those are, I'm getting those numbers from the chart up here. So I've got, that's my 2, and there's the 1. And then in 1 mole, there's 18.01 grams of H2O. Notice I've got 1, 2, 3 sig figs. My answer is going to be 11.3 grams of H2O. So I hope that gives you a start on this. You'll be practicing a lot more of this in the next section because it's all going to be building on itself. You're going to be doing this method, especially grams to grams, quite a bit.